Good day, dear friends. My name is Evgeny Proskrin. I'm the founder of ATF Group. This is an engineering and manufacturing group of companies that started in a garage, producing hardware for transformers. And now it offers digital solutions for a wide range of industrial sectors. Today we are launching a series of micro lessons to share practical knowledge and help our energy sector operate more reliably, efficiently, and safely. After all, our mission is simple: your energy under our protection. In the last video, we discussed what transient processes are and why transformers experience large inrush currents when energized. Today, we'll continue the topic by learning how to reduce inrush currents, which switching schemes are used, and how transient behavior is modeled. There are several ways to reduce inrush current. Choosing the switching moment carefully, ideally at the voltage zero crossing. Eliminating residual magnetization, using demagnetization procedures. Soft start, through series reactors or dedicated starting devices. Staggered energization, energizing one phase first, then the others. Think of it like a car. If you floor the gas pedal, the car jerks forward. But if you accelerate gradually, the motion is smooth. A transformer behaves similarly. A sharp energization creates a current spike, while a controlled start keeps it safe. Safe switching schemes take into account both the phase of voltage and the sequence of contact closure. Symmetrical switching. All three phases close simultaneously, preferably at voltage zero crossing. Asymmetrical switching. Each phase is energized with a time delay to reduce peak stress. Switching through a reactor temporarily lowers voltage and limits inrush current. Fun fact: smart breakers can wait for the optimal voltage phase angle before closing. This is especially useful at high voltage levels. Inrush current can be estimated with simplified calculations. The key factors include nominal transformer current, peak magnetic flux, residual flux in the core. If switching happens at the worst-case phase angle, current can reach 10 to 12 times nominal, but with proper phase selection, it can be limited to just 2 or 3 times. Today's modeling tools allow engineers to simulate transient behavior in detail. They use platforms like EMTP, ATP, and PSCAD for grid-level analysis, ANSYS Maxwell or COMSOL for electromagnetic simulations, and digital twins, real-time models fed by sensor data. It's like a driving simulator. Before getting into a real car, you can test what happens in any scenario. A transformer twin does the same for electrical events. Here's a real example. At a thermal power plant, a smart transformer startup module was implemented. It calculates the ideal moment for switching. This reduced inrush current from 9 times nominal to just 3.5 times. It also alerts the operator if the switching angle was suboptimal, which could lead to another current spike. Transformers are protected by instantaneous current relays. They trip when a current threshold is exceeded. Thermal relays. They monitor winding temperature. Transient analyzers. They track switching behavior in real time. Modern systems may also include automatic inrush compensation using bypass circuits or delayed switching. Now it's your turn. You're working with a 160 megavolt ampere transformer. Its rated current is 900 amperes, but during improper switching, the inrush current reaches 10,800 ampere. That's 12 times nominal. How would you reduce it to 4 or 5 times nominal? What technologies and switching schemes would you use? Write down your solution. We'll review it in the next video. Today you've learned how to reduce inrush current during transformer energization, which switching schemes are effective, and how digital models and AI support safer transient operation. In the next module, we'll cover magnetic losses in transformer cores. You'll learn how magnetic circuits are built, what types of losses exist, and how they affect transformer efficiency. Want to explore the topic in more depth? Visit our website. The link is in the description. Interested in real-world solutions and industry challenges on this topic? Contact us. Our details are on the screen. Want to become a part of the global energy flow? Reach out to us. You'll find our contacts on the screen.